Okay, so today's objective is we will learn what is matter, which we actually learned a little bit yesterday, how it's classified, and how it changes. Okay? So we are doing our notes for today on page 29 of our notebook. Okay, it is Cornell Notes. Technically, the essential question, or what we're being asked, is what does matter, how is it classified, and how does it change? By the end of this period, you should be able to describe the similarities and differences between the different states of matter. So our focus today is how solids, liquids, gases, and plasma are different. Okay? But we will get a little bit of overview of matter altogether. Okay? Now, let me remind you, when you are taking notes, remember, you're not trying to write every single word that's on my overhead. Okay? You are paraphrasing, you're writing in your own words. You're shorthand writing, meaning text language writing. Okay, so use some abbreviations, because I'm going to keep going. Now, don't worry, because this lecture will be online if you need to listen to it again. I know y'all love my voice. That's such a beautiful voice. Okay, so what we're going to look at today is we're going to look at what is matter. So start off, we're going to look at how we classify matter. And we talked a little bit about it yesterday, and it's part of our warm-up today. Okay? First of all, let's review what matter is. Okay? What is matter? Yes? Very good. Anything that has mass and takes a space. Okay? So, yesterday we did an activity where you looked at examples that were matter and examples that were not matter. Remember that? Okay, Maria, can you give me an example of matter? Anything that's matter. An actual example. An eraser. Okay, an eraser. Tatiana, could you give me an example that is not matter? Okay, fire. Remember yesterday some of you were thinking, I don't know if it's matter or not. And remember, fire is not, because even though it does take the space, we can't measure the mass. Therefore, it's not matter. Okay? So for matter, you just need to remember that if you can measure its mass and you can measure its volume, then it's considered matter. Now, yesterday, whenever we did our concept map, we looked at how matter is basically broken down into two major things. The first one that we're going to talk about today is mixtures. Mixtures have more than one kind of matter and can be separated in physical means. So that's important. Can be separated by physical means. So when we talk about physical means, we're talking about physical changes, which should be reviewed from previous years. A physical change can be such as sorting. Like, for example, if you have a salad and you don't like tomatoes, can you take the tomatoes out? Yeah, that would be sorting. That's physical means. Okay? And by the way, if you don't like tomatoes, then you shouldn't be eating ketchup, because ketchup's made of tomatoes. Okay? Filtering. Okay? If you have ever seen your mom cook and she uses a sifter because she wants to separate big pieces from little pieces, okay, that's filtering. You're basically sifting and separating by size. Heating. Okay, I didn't tell you this, so don't tell your mom I told you this. If you ever make Kool-Aid and you want to get the Kool-Aid back, in a very nasty form, okay, put the Kool-Aid on the oven, let the water evaporate, you're going to be left with all the sugar, junky stuff in there, and she's going to have to clean the pot, so don't tell her I told you to do that. Alright? So there's different ways to separate. Those are all physical means. Now, yesterday we talked about how there are two different types of mixtures. And the two major types of mixtures are homogeneous mixtures, heterogeneous mixtures. Homogeneous Homogeneous mixtures are the same throughout, meaning they look the same. Remember, the prefix homo means same. Examples, milk, lined paper. The paper that you're writing on right now, if it didn't have lines, it would be considered a homogeneous mixture because you can't see the different parts that are in there. Now, homogeneous mixtures sorry, that's going to come off in just a second. All right, homogeneous mixtures are also called solutions, okay? So these are also called solutions. You need to make sure you know that. Heterogeneous mixtures are ones that you can see the different parts to it, okay? Those are, examples of those are like chicken noodle soup, trail mix. These are also called suspensions. So suspension is a type of heterogeneous mixture. A solution is a type of a homogeneous mixture. Remember that we also use, even though water is H2O and we think of it as a compound, water can also be a homogeneous mixture. It's a solution because it has some other stuff in there. Alright, so mixtures can be separated very easily. Heterogeneous mixtures, you can see the different parts. Homogeneous mixtures, you can't. They can still be separated, but you can't see the parts. They look the same throughout. Okay? Now, then we go over to substances. Substances cannot be separated by physical means. If they can be separated, it's going to be chemical. If you can separate the substance, you're going to change what it is. Okay, it's not going to stay the same. It's going to have different properties. There are two types of substances. You have elements and you have compounds. Elements are made out of one type of matter, gold, helium. Okay? And where are you going to find elements? Where do you find them? Where do you go look for them? Periodic table. So these are always, there should be a note there, are on the periodic table. Compounds are made out of two or more elements that are chemically combined. So there's two more, but these are chemically combined. So these can be separated, but they're separated by chemical changes. Examples of that is table salt, which is NaCl, sodium and chlorine bonded together. H2O, hydrogen and oxygen bonded together. And those are compounds, and we can separate those. I can separate H2O, but when I separate H2O, that changes the compound altogether. Let me give you, or explain that. H2O, it's water, right? All right, so if there's a fire, what am I going to throw on the fire? Water. Does it put it out?
Sometimes.
Okay, if it's a regular fire, not an oil fire. Yeah. It's going to put it out, right? Okay, water basically puts out a fire. If it's an oil fire, that's a different story. Okay? But if I have a piece of paper that's burning, can I put fire in and it's going to put it out? Yes. Okay. Now, if I put a tremendous electrical energy through that H2O, through that water, it's a very, very high amount of energy through that high H2O, through that water. I can separate the hydrogen from the oxygen. I will end up with hydrogen gas and oxygen gas. Okay? You're like, oh, that doesn't matter. But what you don't understand is that when you do things like that, you change the properties altogether. If I have a fire and I put water on the fire, it's going to put it out. If I separate H2O into hydrogen and oxygen, I just made two gases that are flammable. So together they put out fire. By themselves, they can make fire. Okay? So do you see how if I change this, if I separate these, I change it completely. Table salt. Don't you put it on your food? Okay? All your food has salt, even if you don't put it on. It all has salt. It has natural salt. But some of us, including myself, like things a little saltier, so we put salt on our food, correct? If I separate that and I get sodium and chlorine, I get chlorine, which is poisonous, and I get sodium, that's a metal. So I'm putting basically two elements that one's a metal and one's a poison on my food. It doesn't kill me. Too much of it might be bad, but it doesn't kill me. Together, it's okay. Separate, it would be bad. So whenever you have a compound, if you separate it, you change it to totally what it is. Now, a mixture, if you separate it, really not changing what it is. If I have a salad and I separate the tomato from the salad, does it change the tomato? No. Does it change the salad other than the taste? No, right? So in mixtures, when you separate them, they basically are the same thing. In substances, if you separate them, you change totally what they are. Okay? Any questions over the differences between a mixture to a substance? Okay. All right, so moving on. All right, now measuring matter. Now guys, this is the time that you really have to think about it. Didn't we already have notes on measuring? Yeah. Would you have to write this again? Do you already have this somewhere in your notebook? Yes. So whenever you get to a part where we already have some notes, you probably just want to put in your notes, see measuring notes on page so-and-so if you want to put the page. All right, well, let's review. When we look at measuring matter, the definition of matter is anything that has mass and takes up space. So, if matter is anything that has mass and takes up space, then you obviously are going to be able to measure that. Okay? When you measure that, you have to use specific equipment. So what is the equipment that you would use to measure matter? Graduated cylinder to measure what of matter? Volume. Okay, and triple beam balance to measure mass. Very good. Alright, so you just need to make sure that when we do measure matter, that you measure it correctly. So whenever you're measuring with the graduated cylinder, you always remember how to use it correctly and how to read to the bottom of the curve, which is called the meniscus. Then, when we measure mass, we use the triple beam balance to do so. All right, I want to have a stopping point right now. Okay, I'm going to give you 2 minutes to discuss with your elbow partner, and then 2 minutes to go through and write a general statement, a generalization about the notes so far. Okay, that's what I did in sticky note. So talk to your partner, and then together come up with a general statement for the notes so far. Okay, so you have 4 minutes altogether. Do so now. And I'm putting another pair of sticky notes on your table for the next section of the notes. Okay, we're not done.
she taught this like 3 times. And she has a 16, but I think she taught this like 4.
Yes, it's just a general statement.
What's the second one?
You're just doing one general statement.
Oh, it's
That's for our next section, yes. Yes, the second sticky note I put on your table is for the next section. We're not done with the notes. As I'm walking, I'm seeing that several of you are pretty much to the bottom of the page. So you're probably going to go ahead and get a piece of paper out, and you're going to do a full page. Good. Don't forget to put them in your notebook again. Okay, looks like most of you have your general statement, so I think we can go ahead and move on. Okay, so up to this point, we have talked about mixtures and substances, okay? One of the things that you need to be able to do is you should be able to distinguish between elements, compounds, homogeneous mixtures, and heterogeneous mixtures. Okay? So, Jesus, if I say cereal with milk, what would you consider that to be? Element, compound, homogeneous, or heterogeneous? Very good. Would it be a heterogeneous mixture, guys?
Yes.
Yeah. Because can we separate the milk from the cereal? Yes, and we see it, correct? Okay. Menard, if I say salt, which is NaCl, sorry. A compound. Okay? And then I give you this example. If I give you examples, you might want to know those. Okay? What if I say, Xavier, if I say carbon? That would be an element. So you see how I can give you something and you should be able to tell me which one of those it is, right? Okay? So you need to understand those 4 to that level. Okay? Now, we're going to go ahead and move on. So now we're going to look at our focus, which is the states of matter. But before we look at the states of matter, we need to figure out and review what is matter made out of. Well, matter is made out of atoms and molecules, depending on what it is. If it's an element, it's going to be made out of one atom. If it's anything else, it's going to be made out of molecules. And molecules are actually made out of atoms. So, an atom is basically the smallest possible particle of any element. Any element on that periodic table is made out of one specific type of atom. Okay? And we know that atoms exist by indirect evidence. Indirect evidence means that we know from basically processing and thinking about it. But truthfully, nowadays we can actually have some really good electron microscopes that we can see pretty well sort of what the atom looks like. Okay? So atom is the smallest particle of any matter. All matter is made out of that functional unit. Okay? A molecule is the smallest amount that you can have of a compound. So an atom would be one hydrogen atom. A molecule would be H2O, one molecule of H2O. Okay? All of these is what makes matter. And when we talk about the states of matter and how they act, we're actually talking about how these things that are the building blocks of matter, how they act. Okay? So, we're going to move into the states of matter. Alright. So there are 4 states of matter, and the energy increases, or actually, the kinetic energy increases as we go from one to the next, because the speed of how the particles move change. So let's start off with solid. A solid is something that has definite shape and definite volume. So that's important. Remember we talked about that your special assignment is going to talk about characteristics? This characteristic, definite shape, definite volume of solid. The particles in a solid vibrate in place, so they move. That desk that you're sitting at, you're thinking it's not moving, it's moving. The reason you can't feel it is because it's a very small movement and it's a very fast movement and you can't really pay attention to it. Okay? Plus, particles are very, very tiny. And basically, in a solid, you really don't have a lot of movement of the particles. Okay? So, if I have this cup full of marbles, okay, this is representing my solid. Okay, this cup full of marbles represents my solid. So if I think of how these particles are moving, if I go like this, are those marbles shaking inside? Yes. Will this marble at the bottom ever get to the top? No. No matter how much I shake, no matter what I do, it's going to stay where it's at, right? But they're moving. That is how the particles of a solid move. Is they vibrate and shake in place, but they can't move positions. Okay? Because that's how they move, therefore, they have a definite shape. Okay? Regardless of what I do, the shape stays the same. Correct? So it has a definite shape, and it has a definite volume. It takes that certain amount of space no matter what. So if I take any solid in this room, let's say I take this, and I put it at this table, and I leave it there forever and ever and ever, nobody takes a piece of paper anymore, we're going to forget about weathering, erosion, rotting, all that. None of that. None of that happens. It's in this case, and it's not going to happen in nothing. Will it ever change? No. Because the particles in here are shaking, but they're not going to do anything else in that. So, it has definite shape, it has definite volume. Then we move on to a liquid. In a liquid, the particles move a little faster. Okay? So you have a little faster movement, and they can flow over one another. Therefore, it has no definite shape, so it can change shape, but it does have definite volume. So, if the particles of a liquid have a definite shape and definite, does not have a definite shape, but it does have a definite volume. Okay, so if I take these marbles out of here, okay, this represents my liquid. If I put my hand over it and I start doing this, can those marbles move past each other?
Yes.
Yes. Okay? The marble at the bottom can end up at the top eventually, right? Alright. It has this shape right now. If I put it into a box, does it take the shape of the box? Yeah. Aren't the marbles going to spread out to fill in the box? Yeah. So it's going to take the shape of the box. If I throw them on the floor, they're going to roll out. And if nobody kicks them, they stop at a certain amount, and that's it, right? So think of a liquid. If I take a bottle of water and I spill it right here, it's going to spread out. So is it the same shape of the bottle that it used to be in? No. But is it the same amount of water? Yes. So it's still going to take the same amount of space. So it does have shape, a definite shape, but it does have definite volume. And the reason for it is because the particles can spread out a little more. So here you had solids. Shake, 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 shake. Then you have liquids. They can flow a little more. Okay? Then we're going to a gas. A gas has molecules that move very, very quickly. Okay? And they can separate or get really close, depending. So basically, in a gas, you have something called expansion or compression. So in a gas, those molecules can expand or they can compress. They can get really close together or they can get really, really far apart. And because of that, gases don't have definite shape and they don't have definite volume. Because of the fact that they can get really, really close together and get really, really far apart. So, this is my example of gas. Here I have a bunch of balloons filled with air. Isn't air a gas? Okay. So right now, I kind of push them before they pop. And they take this amount of space, correct? Alright. So if I open this, and I let it all spill out, what's it going to do? They're going to go everywhere, correct? Do we know that for sure? Are you positive? Okay, so if I let it go, are they all going to spread out?
Maybe.
Now, they had helium. They'll fly everywhere. If I open the door, can they eventually float out of this room?
Yes.
Yes. The reason for it is because the molecules are moving much, much faster. So you're going from a solid, check right here, to a liquid, it flows a little more, to a gas, it flows everywhere. Okay? And it can spread out really far apart or really close together depending on if you compress it or not. Okay? So, since these are the three, we're going to talk about plasma in a second. But these are the three major ones. Let's now talk about energy. Okay? So I'm going to bring two words in that are physics words, not chemistry words. Potential energy and kinetic energy. Does anybody remember from last year or the year before what potential energy is?
Potential energy is stored energy.
Okay, potential energy is stored energy. So can someone else tell me what kinetic energy is? Yes. Sorry? Movement. Very good. So I have potential energy that is stored, and I have kinetic energy that is moving. Correct? So let's talk about kinetic energy. So I'm going to put kinetic energy. So how much kinetic energy does this have? A lot or a little?
Little.
So little. Compared to the gas I put over here. Now, how much kinetic energy does that one have? A lot. Okay. So now we look at potential energy. How much potential energy does this one have? A lot. And how much potential energy does gas have?
Little.
So, listen to my question. What happens to the potential energy as it goes from solid to gas? Yes?
It starts to get used.
I just need decrease, increase. What happens to potential energy as it goes from a solid to a gas? It decreases. Very good. Okay? So, Ivan, can you tell me what happens to kinetic energy as it goes from a solid to a gas? It increases. So, potential and kinetic energy are going to be inversely related. Inversely related means opposite. Okay? So, any questions up to this point on energy? You must know, out of these three, the characteristics, and you have to know specifically what are their energies doing. What is the potential energy? What is the kinetic energy doing? Okay? So when we're looking at pictures in a solid, you would have particles that are really close together, correct? And what is the type of motion here? Just vibrating. Alright, then I have a liquid. In this one, I have a little bit more separation, and they can move in different directions, right? Alright? And then a gas, I'm just going to do it over here. They can be very, very separated, and they can move basically anywhere they want. Correct? Okay. So, now let's look at plasma, because that's the one that y'all really haven't talked about in other classes. Right? So, plasma is the highest energy state. Okay? Highest energy. And it is the most abundant in the universe. If you were out looking for which state of matter could you find the most of in this universe, and it would be plasma. Plasma is very high energy. The particles are going crazy. They're moving crazy fast. Okay? And we here on Earth can find it in lightning. Lightning is made out of plasma because it is superheated air. So think, if I have, let's say we think of water, okay? We have ice as a solid, correct? We have water as a liquid. We have water vapor as a gas. And that water vapor that's up in the air along with oxygen and all that other stuff out there. Whenever there's an electrical charge that is created by a lightning storm, it superheats the air and that water vapor. It superheats it. Basically, it gets really, 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 really hot. And it makes it go into the plasma state. That's what you see. That's basically what you're seeing. You're seeing the release of heat because of friction. Because that air is moving so fast and creating so much friction that it causes electricity and causes the lightning. Okay? So lightning, technically, is plasma. And that's the only place we're going to find plasma. Other than some other laboratory equipment and so on. Okay, your plasma TVs are not made out of plasma. Okay? The sun, any star is made out of plasma. Superheated material. That's what's the most abundant, because how many stars are out there? Trillions and trillions and trillions, right? And every single star out there is made out of plasma. That's why it's the most abundant. Okay? I saw a hand up there. Question?
So like lightning is its friction, so it's like the spark.
Yes. So lightning is basically the spark of the energy coming off of all that air moving that fast. It's just creating friction. Okay? All right. So any questions over the 4 states? Properties, anything like that? Okay. So now we come to how it changes. Matter changes in a variety of ways. These you should know except for maybe one of them. 4 of these you should know. So technically, this should be very easy, and you really shouldn't have to write a lot. You should write what you don't know, right? Everybody in here has seen ice cream melt or ice melt, correct?
Yeah.
So, when a solid turns into a liquid, that's melting. That's what the process is called. Which means that on the test, no one's going to get that wrong, correct? Because everybody knows what melting is. Now, you have to add one more thing. What happens to the kinetic energy here? Decreases or increases? Increases? Yes, because isn't it moving? Yeah, okay. Evaporation, you're going from liquid to a gas. Everybody in here has seen things evaporate. Okay? What's going to happen to the kinetic energy here? Increases. Condensation is a gas to the liquid. What's going to happen to the kinetic energy here? Decreases. Freezing is liquid to a solid. What happens to kinetic energy here? Decreases. And the only one that I think that you probably did not know is sublimation. Sublimation is the state of the change in state of a solid directly into a gas. So usually when we think of ice, it melts first. It goes into a liquid phase. Then it evaporates and goes to gas phase, right? There are some solids that don't melt, they sublimate. And what they do is they go from a solid state directly to a gas state. Everybody in here has seen that happen or knows about it. Okay? Who has, when you've seen it? Yes? Dry ice. Ever heard of dry ice, right? Okay? An example of this is dry ice. They call it dry ice because it doesn't get wet. The reason it doesn't get wet is because it sublimates. Dry ice is not water. It's not H2O. It's carbon dioxide. It's carbon dioxide in its solid form. Then it doesn't go to the liquid form. It sublimates and it turns that solid into the gas. That's why it's called dry ice. Okay? Now, what happens to kinetic energy here? It goes faster and increases. Very good. So, you're responsible for knowing the 4 states of matter, okay? Their characteristics, how the particles move, what type of energy they have, okay? And then you are responsible for knowing the changes, but specifically, because everybody knows those 4 changes, specifically you need to know what happens to the kinetic energy as you go from one to the next, okay? So, what I want you to do is, once again, I want you to discuss. Now, these are the end of the notes. So I want you to compare notes. Look and see if you missed something important. Okay? Then come up with a generalization. So on these notes, how many sticky notes do I need to see on these? 2. Very good. So go ahead and do that now.